Limits at Infinity Part 3. In Part 3, we're going to start off by talking about the squeeze theorem. We'd like to find the end behavior of y equals sine x over radical x. To find the end behavior of that, we're going to need the squeeze theorem. Recall that the first thing we need to do is to figure out what two functions we can squeeze sine x over radical x between. We need to squeeze it between two functions. Well, look at the numerator, sine x. Sine x is always between -1 and 1. And so sine x over radical x will always be between -1 over radical x and +1 over radical x. So we've now squeezed our function between two other functions. Well, what's the end behavior of those two functions? Well, as x gets very, very positive, -1 over radical x gets closer and closer to 0. And +1 over radical x also gets closer and closer to 0. So they both get closer and closer to 0. Well, if the thing on the left gets closer and closer to 0, and the thing on the right gets closer and closer to 0, then the thing in the middle, as x gets larger and larger, the thing in the middle also has to be getting closer and closer to 0. So now that we know that sine x over radical x gets closer and closer to 0, we can discuss something like 5 plus sine x over radical x. And remember, because the two limits exist, we can say that the limit of the sum is the sum of the limits. Then notice that 5 really doesn't care what x is doing, and so the limit of 5 is just equal to 5. And we know that sine x over radical x, that's getting closer and closer to 0. So the overall expression is getting closer and closer to 5. And we've got a graph of that. So you can see the horizontal asymptote of 5, but can you also see how the amplitude is getting smaller and smaller? And that's what taking sine x and dividing it by radical x does. Dividing by radical x means that that overall expression of sine x over radical x is getting a smaller and smaller amplitude. All right, so we're going to finish up by just reminding ourselves what we know about polynomials. If you want to study the end behavior of polynomials, you really need to remind yourself of your basic monomials. X squared, x to the 4th, x to the 6th. They all look like just a cup, a parabola. They all have this same similar shape. And your odd exponents, x to the 3, x to the 5, x to the 7, they all have this shape where it looks like one of the arms fell down. So if you're going to do something like this polynomial here, if you recall that when you discuss end behavior, the guy who becomes most important in the discussion is the guy with the highest exponent. He becomes so much the discussion as x gets larger and larger. And so when you look at end behavior, you only need to look at him. So the leading term here is -2 over x to the 3. So what does y equal x to the 3 look like? Then we take into account that it's a negative coefficient. So you just take y equals x to the 3 and flip it about the x-axis, and that gives you the graph of y equals -x to the 3. And y equals -x to the 3, what you do is you just look at that end behavior. So what happens as x gets more and more positive? Well, as x gets more and more positive, -x to the 3 gets more and more negative. And as x gets more and more negative, negative x to the 3 gets more and more positive. And since the leading term is really the only term we're interested in when we discuss end behavior, we say that as x gets to positive infinity, the overall limit is negative infinity, and as x gets closer to negative infinity, the overall behavior is positive infinity. And if you look at a graph of this, you can see that the graph has pretty much the same shape if you zoom out far enough. So that ends our discussion of limits at infinity, and have a great day.